We'll now move over to the last presentation and session on maritime research. We have two eminent scientists in this session, Mr. Gopkumar K, Scientist G, Deep Sea Technologies, National Institute of Ocean Technology, Chennai, Ministry of Earth Sciences, Government of India, and Dr. Arnab Das, Founder and Director, Maritime Research Center, Pune. The session convener for this is Captain Ajay Achyutan, MD, Synergistic Solutions. I would like to hand it over to him. Thank you.
Well, thank you, Padma, and good afternoon, everybody. Maybe you want a small stretch break after that amazing session where we're going to. So maybe we can just take a small deep breath and just get active, because we are entering a totally different domain now. Thank you, Informa, for giving me the opportunity to chair this session, moderate this session. It's a privilege to be part of the advisory board of Informa for the last decade. People at sea from a mariner background normally have what's called as, they say the people ashore have got sea blindness. But one area where both people ashore and people at sea seem to be blind is the underwater area. So the underwater domain awareness, and we have sailed over the water, but what was underneath it? The first time, though we are all present to it, it really gathered my importance when we saw the syllabus for the extra masters which Captain Jay Kumar, nautical advisor, created. And it amazed me that there's so much more we could do, so much opportunities. We have used something like baseline, territorial sea, contiguous zone, EEZ, EFZ, high sea and all. But the first time in Unclosed, I saw a chapter called areas. And प्यार से उसको ABNJ बोलते हैं, areas beyond national jurisdiction. And what is called the National Seabed Authority. So what is out there below the sea? On getting this project of moderating this, I just did some initial research and found there's something more than gold out there, and people are going to share with you, these two wonderful gentlemen, Dr. Gopkumar and Arnab Das. But while they were looking at it, I also want to share some concerns, and maybe I hope they address that. Is while we are going to explore and exploit what is under the sea for the sustenance of humanity, we have food and energy, will our explorations and exploitations sustain the earth and life on earth? So I'll first introduce Dr. Gopkumar, Scientist G, is the NIOT. I had a wonderful chat with him yesterday. He's worked with the Indian Navy for about 23 years in the marine engineering operations, research and development and planning. He joined the National Institute of Ocean Technology, NIOT, Chennai on deputation in 2013, followed by a permanent absorption, leading the project team working on the developing deep sea mining technology under the PMN, that's the polymanganese nodules program of the government, to harvest polymetallic nodules, that's another name for it also, from the depths of oceans up to 6,000 meters. He also leads the trial team in testing at sea and deep sea mining equipment and systems developed. As the chief scientist, he led the team in the recent undertaking the successful and deepest trials over 5,000 meters depth in central Indian Ocean, and in-house developed self-propelled seabed mining system. So over to you, Dr. Gopkumar. We're really looking forward to these two sessions.
Thank you, Captain Achyutan, and for that extensive introduction. And thank you to the organizers for this forum. I will quickly go on to the presentation and share my screen.
So while he is sharing the screen, let's please acknowledge all the participants here, and please do feel free to put your questions in the chat and we'll try to address them. If not, I take personal responsibility to note down the questions and get answers to you.
Captain Achyutan, are you able to see my screen?
Yes, yes.
Yeah. So my topic is developments in deep sea mining technology, and I'll cover towards the end related opportunities which may be of interest to this forum. I will cover up this topic under the 4 heads. Blue economy, because that's the talk of today's economy, and it's closely related to mining. Overview of ocean minerals and mining technology. What work we have done in India on this particular area of deep sea mining and related opportunities. Before we go on to this aspect, I think it's the fitness of things to just refresh, though many of you being seafarers are aware of the various zones that any independent country has rights over. So there are two key words. One is the exclusive economic zone and the area. Now, the exclusive economic zone is where a country has sovereign rights over the water and the continental shelf, but not so much any navigational authority over the water, but it has sovereign rights over the water column in terms of exploitation of resources and the seabed. And in case you have a continental shelf which extends, you can go up to 350 nautical miles. Beyond 350 nautical miles, one is you're in the high seas, and the land area or the seabed does not belong to you. It is under the authority of the international authority, and there is a body called International Seabed Authority who owns this area. So in case you want to do anything there, you have to take their permission and their prior approval. This comes from the understanding that all the seas beyond your economic exclusive zone belongs to mankind. It's a common heritage of mankind. So the resources belong to everybody, and the need to protect also belongs to everybody. With that, India has a very, very large exclusive economic zone, principally large because we have a lot of island territories, which gives us this extra EEZ. We have a 2.172 million square kilometers of area with a coastline of 7,500 kilometers. Now, in this exclusive zone, you have rights over all the resources, living and non-living. You can harness energy from the wind and the seas there. You can conduct marine research, and you have a responsibility to protect and preserve the environment too. Under the UN Sustainable Development Goal, SDG 14, that has come out for the decade, which says that you should not only conserve, but you should conserve and use it in such a way that you're able to sustain the development also with those resources. So with this, broadly, the blue economy encompasses all the economic activities that is related to the coast, seas, and the ocean. And it comes with the adage that it should be in a sustainable manner. When we say sustainable, that you can sustain it, first of all, your events, your impacts are reversible, and you can do it over a long period of time, giving nature a time to recover. Now, what are the economic activities that is related to the seas and the oceans and the coast? Shipping, marine logistics, tourism, harnessing of living and non-living resources, which comes to food, fisheries, aquaculture, and even bioprospecting, offshore mineral exploration and mining, freshwater and energy from the wind and the seas, and of course, coastal preservation and protection. This is a very, very serious issue now going to affect and also affecting many of our coastal areas. Marine scientific research with a lot of stress on climate change and its impact. And importantly, marine pollution, that is both coastal pollution and the marine pollution which occurs at sea. And just to give that there are so much of plastic in the ocean that even the Marina Trench is not saved from those microplastics. All these blue economy aspects have been worked upon at NIOT here at Chennai, where we have gone into wave powered navigation lights, water from the sea, desalination plants for the Lakshadweep Islands. We have been providing for the last many years. Deep water submersibles up to 6,000 meters. We have a ROV. We are developing a manned submersible. We have shallow water ROVs which have been used extensively in the coastal mapping. We are the principal agency for data buy program of the Government of India, which is used for the data collection for cyclones, climate change, and many other things. We also have a very thriving marine biotechnology department, which looks at both medicine as well as using for commercial purposes. And coastal protection is also one of our work areas. To give impetus to the blue economy initiatives, the Government of India, under the nodal Ministry of Earth Sciences, has brought out a deep ocean mission in June 2021 with an outlay of 4,077 crores, where these are a few of the important missions to be achieved over the next 5 years. Deep sea mining, one of the flagship programs, and development of a 3-man manned submersible which can dive down to 6,000 meters. These are very useful for exploring and harnessing of deep sea minerals and energy. Development of ocean climate change advisories, exploration conservation of deep sea biodiversity, including bioprospecting, ocean survey and exploration of sulfides from the Indian Ocean, energy and freshwater from the ocean, setting up of advanced marine station for ocean biology, and above all, to spread awareness and do capacity building within our country. These are the things which actually go a long way in leveraging our blue economy initiatives. Having said that, I will give you a brief overview of the resources or the minerals from the sea. I will address only the non-living resources from the sea. While on the coast, you have the placer deposits. You have examples of monazite sands off the coast of South Tamil Nadu and Kerala, phosphorites off the coast, both in India as well as abroad. In fact, New Zealand has a very, very rich phosphorite deposits. Tin mining has been done in Indonesia very successfully over the last many years. Diamond mining, in fact, most of diamonds today come from the shallow waters of Namibia and South Africa, and they're all harvested on depths of about 50 to 200 meters depth. The three principal minerals from the sea, which occur in the deep ocean, are the polymetallic nodules, which we call as PMN, the seafloor massive sulfides, which are called SMS. They are also called as polymetallic sulfides, which also predominantly occur at the undersea volcanoes and mid-ocean ridges, wherever there are intense hydrothermal vent activity. Then you have the cobalt-rich crusts. Why they are called cobalt-rich? Because they're rich in cobalt as compared to many of the other sources. And these are found typically on deep sea mounds and ridges where sedimentation is not very high. And we have the one of the interesting energy sources, that is gas hydrates, principally of methane, which are found in sediments. And India has a very high deposits of gas hydrates. To just give expanse of how they look from the coast to the deep waters, if you start from the right-hand side, which is the coast, sand, gravel, mining has been going for many years, placers, phosphorites, and as you go down, you find on the continent rise, the gas hydrates in sediments at about depths of 800,000 meters. And as you go further down to the abyssal plains of 4,500 to 5,000 meters, you have the manganese nodules strewn across. What you see in blue is actually from one of our submersibles photographs of nodules in the Indian Ocean. Then you have the seamounts on which you have cobalt crusts, followed by, if you go further to the left, you have on the ridges and the mid-ocean ridges, you have this, wherever there are hydrothermal activities, you have this polymetallic sulfides. The start of, or the origin of nodules has been with the Challenger expedition in 1873, where during the oceanographic expedition off the Siberian coast in the Kara Sea, they picked up very peculiar black objects, which were later identified as manganese nodules. And in 1965, Meros proclaimed that within 20 years, we are going to have a very, very thriving commercial activity. But still in 2022, or rather 2022, from so many years, we are still to reach that target of very, very active activity in this nodule commercialization. Just to give everybody an overview of what, how, and where they are formed. These occurs at depths of 4,000 to 6,000 meters on the abyssal plains. They are present as nodules. In fact, they are strewn on the surface and a little bit subsurface. So they are easy to collect, easy to identify, and they accrete very slowly over millions of years. There is a seed. The seed could be a shell, a rock, or a bone piece which descends from the surface. And around this, these slowly develop as potato shapes. What you see here, they are from 5 mm to 70 mm. And many times, especially in the northern part of our Indian Ocean, you find that they all joined together, some of them into sizes of more than 120 mm also. They have very, very thriving living beings resident on these nodules, and which form as the habitat for at those depths. These are very, very rich in copper, nickel, and cobalt as per where they're available. And in the Pacific Ocean, as you will see here in the next slide, in the Pacific Ocean, they're also rich in the rare earth elements. You can see the table which is brought out. So CCZ is the Clarion-Clipperton zone, which is area in the North Pacific between Hawaii and Mexico, which is one of the most extensive and the most rich areas of nodules. They have 15 kg per square meter abundance. Then you have Peru, good, but not as interesting in terms of metal content. Then your Indian Ocean, which is also very interesting, but the abundance is slightly less. It's about 5 kg per square meter. And then you have the Cook Islands, again in the Pacific Ocean, which is extremely rich. In fact, though it's written here 5 kg per meter square, they have actually now from prospecting come to a realization it's about 20 to 40 kg per square meter, very rich in cobalt and also rich in rare earth. So today's interest areas for polynodules are actually the CCZ, as the Clarion-Clipperton zone in the Pacific, and the Cook Island and the islands in those areas. These are the seafloor massive sulfides. occur at depths of 1,000 to 4,000 meters as per the location of the mid-ocean ridges. And they are extremely rich in marine biodiversity. In fact, they are a self-sustained ecosystem with very little sustenance from the sunlight on the top. In fact, they make the food available is from the hydrothermal vents that comes out, and they're rich in copper, nickel, and the attractions actually derive from the content of gold and silver in that. These are the occurrences of these deposits. Many are still to be traced, but they are known to be in these mid-ocean ridges. This is the area that brings out the identified locations across the world. Interesting thing to understand or to note here is Papua New Guinea actually had a very well explored and documented sulfide deposits called the Solwara 1, where actually the deep sea mining should have been kick-started a couple of years back, but for reasons which I'll explain subsequently, it had to be shelved. So this particular area has not been touched because of a lot of environmental environmental protests about the deep sea mining to be started here. Cobalt-rich crusts, these are basically plateaus where sedimentation levels are very low, but you have this cobalt, ferromanganese and rich in cobalt as layers of varying thickness across the spread. They are on the sides of these plateaus as well as on the top. So though they look very attractive, they're rich in titanium, they're rich in cobalt, and one of the richest sources of cobalt, if you leave aside the terrestrial mines. But they are actually very difficult at this point to actually retrieve and collect and make into a commercial system. But there are a lot of study and research already in practice in this area. Gas hydrates, these are typically ice-like crystals of water entrapped in a low-weight hydrocarbon. It is principally methane, but there are also butane and propane hydrates. But the majority are methane, which form because of high pressure on the seabed and the low temperature, which is in the range of 3 to 4 degrees centigrade. And these are typically formed on the continental rise, about 40 to 80 meters below the sediment. And in India, they are found on the KG Basin, Kerala Konkan coast, Mahanadi Basin, and also in Andaman Nicobar. Otherwise, these are very normal in permafrost regions in the northern hemisphere. In fact, Lake Baikal is a known source of gas hydrates. This gas hydrate program is steered by the Director General Hydrocarbons. NIOT here has a role to develop technology for safe and controlled extraction. Just to give you an overview of the possible mining areas in Indian Ocean, you have the gas hydrates on the top, then you have the in fact, the second one, the cobalt crust. This is a new recent discovery by the Geographical Society of India, where they have found cobalt crust and cobalt nodule presence in the Andaman Seas. Then you have prospect in the Afanasi Nikitin Seamount, south of Sri Lanka, which also is supposedly rich in cobalt. A lot of samples have been collected. And then you have the two areas, that is the polymer nodules and the hydrothermal sulfides, two down below, which are under jurisdiction of ISA, and India has a area allocated to us for research, exploration, and survey. To give overview of what mining system or a deep sea mining system will look like, there are two schematics, both convey the same meaning, but they are given in a different perspective. If you look at the left side, deep sea mining system will principally consist of few components. You have a surface platform, which is a ship, which has to be dynamically positioned. It has to hold position in the same place. It should be stable because it's an open sea with very less safeguards of a bay or a cove or a environment protection. So it's an open sea, and below it is a metal pipe or a flexible pipe which descends to the depth from where the metal has to be collected. And this metal pipe or the riser bundle, as it will be called, not only is a transport medium, it also conveys the power and also the control systems, because since the depths are so large, varying from a minimum of 800 meters to as high as 6,000 meters, everything is remotely controlled. No human intervention is possible at those depths, except intervention from remote. So this riser bundle has the purpose of not only transportation, vertical transportation, not horizontal transportation, and that brings in a new dynamics of flow, and it also has powering. The power can be in many megawatts of power and real-time communication, uninterrupted real-time communication. So it can't be acoustic, it has to be real-time wired fiber optic connections. So you have, if you start from the bottom, the seabed nodules, polymer nodules, which are depth of 4,000-6,000 meters, it is laid down, and you have a crawler or a collector which collects these nodules, sizes it, and pumps it to intermediate station from where it is pumped to the surface. So when the lengths are large, 6 kilometers or 5 kilometers, the pumping pressures required are enormous, and the pipe diameters in the range of 0.5 meter to or 300 mm to 500 mm. These are the pipe diameters. And similarly for the sulfides, you have to first clear the overburden if it is there, and then you can access the mineralized layers. And when you go for the cobalt crust, most of your activity is on the inclined slopes or on the plateaus, and that is where the challenge comes. And you have to actually scrape off this metal, and they are not uniformly distributed. So that is also a challenge. How do you actually maximize your intervention? So the mining configuration typically depend upon the type of resource, whether nodules, sulfides, or cobalt crust, the type of ship you have on the surface, the depth, the terrain where you're going to operate, and the sea conditions, the cyclonic, the winds, waves, etc. I have not talked about the environment part yet, where the environment impact, but I will be addressing as we progress. So to give an overview, what the 4 principal components of a deep sea riser system would, of a deep sea mining system would be a floater, which supports all activities with adequate power. It's capable of handling heavy lift systems. It has deployed this and sustain it. It should be stable in sea state conditions of wind, waves, and swell, maintain position and heading. It has to be dynamically positioned at all conditions and all weather conditions. And it should be able to store some part of the collected material from the seabed. Then there is the umbilical riser system, which gives the powering, communication for real-time monitoring and control, a vertical transport system, not only to transport it vertically from bottom to top, but also as per the environment regulations, you are supposed to return back the same water to the place from where you collected. So it has to go back. So there has to be a downcomer which transported back to the source of collection. And this all this weight has to be compensated through suitable heave compensation systems. Then you have a seabed mining tool, which depending upon the resource being collected as a nodule or a sulfide or a cobalt, you require a seabed preparation in case of sulfides. Otherwise, it's a nodule collection. You can just simply go and suck it up and separate the sediments and pump up the nodules. Subsea navigation is also a very, very important aspect, because you are maneuvering something 6 kilometers down or 5 kilometers down, and you have a ship on the top, which also has to maneuver in tandem with the subsea component. So that is also a very big challenge and requires fair amount of expertise and system involvement. All this comes with the restriction of environment impact. What is the area of impact? What is the area of our activity? The type of noise, sound, light that we would be generating. It's actually an area which has not seen any of these interventions at all for the last probably millions of years. And that is a very, very serious issue, which actually is the protest against deep sea mining. And on board, whatever slurry we actually transport to the surface requires to be separated, and separate so well that we don't lose any of the collected items, because you are spending so much of money and effort and energy to collect it, and then those separated fluid or what are the tailings has to be disposed of in a compact manner back to the source of collection. So this involves a lot of engineering, heavy engineering, and reliable operation. And this, like in oil and gas, offshore oil and gas, once you start operation, you cannot interrupt, because if you interrupt, you will start all over once again. So this is a continuous process over days and months for as much as probably 3 to 4 months at a stretch. In fact, the target is that you should be able to operate at least about 300 days in a year. That is sort of requirement. The most prominent and the successful deep sea mining proven expert exercise that was done was in 1976 by a consortium of companies led by Lockheed Martin. This was a ship, Hughes Glomar, which was a 45,000-ton ship with a drilling rig, which was used to actually connect up the steel pipelines. And what you see on the top right is the miner, which was actually screw type locomotion system, which was used. Actually, the ship was a large dry dock, which was built for some other strategic purposes, and they were able to successfully pump up 800 tons of the nodules in a depth of 4,500 meters from the Pacific Ocean. This was the project in Papua New Guinea, Solwara site, which was actually initiated by Nautilus Minerals. which had to be shelved. It was actually had progressed very constructively and to a great level, but the whole project had to be shelved because of the protest on the environment impact that would have caused by this heavy amount of sediment, the removal of the overburden and the damage to the ecosystem there. So these are the 3 machines that you see on the right hand side made by SMD UK, which are actually ready for deployment, but the whole project had to be shelved. This is another pilot demonstration that was done by Japan in 1917, where they actually put this sulfide mining system and they pumped up pilot slurry to the surface. They used 2 ships actually to do this exercise, one to deploy the mining machine that you see there, and another one which had the implement pump system to pump it to the surface. So this was successful, and they were actually able to validate a lot of the designs and a lot of their functional constraints, with which they are planning to go escalate it to further more larger systems. And interestingly, this does not have any environment protest because it was done in the EZ, not in international waters. This is one of the another successful subsea mining of diamond mining of the coast of Namibia, where you have a large crawler of 280 tons with a huge centrifugal pump, which just lifts up gravel and rocks of 100 mm sizes and pumps it through a vertical pipe, just brute force transport. And this has been going on very successfully for the last many years of the coast for diamond mining. India's tryst with deep sea mining started off very early 1981, 26 January, where the first grab was collected nodules from RV Gaveshni of National Institute of Oceanography. Subsequently, India was also one of the pioneers to be registered as a pioneer investor for deep sea mining with Japan, France, and erstwhile Soviet Union. We were allocated about 150,000 square kilometers by the agency at that time, which was the precursor to the International Seabed Authority formed by UNCLOS, by the rules of UNCLOS, where we given this huge amount of area in the Indian Ocean. We were the only country to apply in the Indian Ocean, whereas much of the rush those days was for the Pacific Ocean in the Clarion-Clipperton zone. This area of 1,500 square, 150,000 square kilometers was extensively surveyed and identified. And as per the contract, we had to return 50% of the area back to ISA. And we were allowed to retain 50%. That means we today have 75,000 square kilometers area. The concept was that you survey and give an equivalent area back to the ISA, which allows the ISA to give to any other developing country who is less fortunate to do this sort of science and technology. So we have 75,000 square kilometers where we identify the first generation mine site. And in 2013, we identified the test mining site where we are going to do the first pilot demonstration test in the Indian Ocean at a depth of 5,400 meters. The contract was renewed in 2017 and we are going to renew it further in 2022 for another 5 years. This is the area in the middle of the Indian Ocean at latitudes of 10 to 16 degrees south to the east of Madagascar. And what you see on the right hand side, the area in black are the ones retained by India, and the ones in red have been handed over to ISBA as the reserved area for any other prospective country who wants to apply and take it. The Indian polymetallic nodule mining program has principally driven by 3 institutes. For survey, exploration, and environmental impact assessment, it is NIO Goa, National Institute of Oceanography. For mining technology development, it is NIOT, National Institute of Ocean Technology, Chennai. And for metallurgy, it is the Institute of Minerals and Materials Technology, Bhubaneswar. There were many other institutes which were involved, Engineers India, HZL, and NML. But as of today, these are the 3 principal institutes which are working on the Indian polymetallic mining program. So at NIOT, first, since as the institute was formed and this was one of the first projects, we actually had to, and we had no prior experience of offshore engineering or offshore deployments. This was our first exercise. So we had to get a grip on the technology, and we started with actually doing sand mining at shallow water depths of 40 meters and then eventually graduating to 451 meters in 2006, where we were able to pump sand through a flexible riser to the surface. So that was a big achievement for us, initial days. And then we had gone for a harvester, a nodule harvester, which is akin to a potato harvester, which is a mechanical harvester to collect nodules from the surface of the seabed. Many others have gone for a suction type harvester, which is a educted sort of pickup system. for the present, we are sticking to the mechanical system because it has less impact on the soil also. Now, ours is a pilot demonstration, not so much as a commercial demonstration. In 2010, we were able to demonstrate integrated trials where of the Malvan coast, we laid artificial nodules because that area does not have any nodules. We had to lay a bed of nodules and we collected it with our mining system and pumped it to the surface to prove the whole system is able to work and our technical concept is validated. So this was the base on which we actually took the leap to go to 6,000 meters of developing integrated mining system. Subsequently, it is also seen that the sediment, the seabed in those areas are very, very soft. So we actually had to assess the seabed before we actually make the mining machine, which is supposed to crawl or move on this surface very reliably and ably supported. So this was a soil tester, in situ soil tester we designed and deployed, which was used in 2011, to actually assess the soil strength. What you see on the right hand, very soft. And what you see the pictures are the nodule bed photograph in that area. So our configuration or our mining system philosophy has been first that we have a mining machine on the seabed which also has a high pressure pump to transport the nodules to the surface. But as we developed it, we realized that the mining machine was becoming very large and very heavy. For the sort of platform we had to deploy, most of our trials are done from our research ship Sagar Nidhi. So we had to be frugal and little weight conscious in our design. So which is when we actually went to the system of two-stage riser system, where we had the mining machine on the seabed, which is just to collect and do a local first level pumping.
Can you summarize also in 5 minutes?
Maybe 5 minutes.
Okay.
Yeah. And you have an intermittent station which pumps up to the surface. So with this system, we said we will do a stage-wise development of a mining machine on the seabed and the intermediate station with the high pumping system. So this is what our system was. We had the mining machine on the seabed with a collector and a crusher and a first level of transport and a high pressure system, which is elevated from the mining machine at a height of 50 to 100 meters, which transported to the ship with a flexible riser system. So these are our progressive trials we did from 2017. We did at 890 meters, first in the Bay of Bengal in a very soft soil, and then we actually did in 3000 meters again in the Bay of Bengal. And we did in 2021, we actually did in the Central Indian Ocean, basin at 5,270 meters, where we successfully were able to test this equipment. In fact, it was validating all our systems of hydraulics, electro-hydraulics, electrical system, power, everything was proved. We were able to run it for about 5 to 6 hours without a hitch and lift it up in a working condition. And this is what we plan to do in the coming year. In fact, this year, where we actually plan to go back to the mining station, do a nodule collection, size optimization, and pump it first level. That is about 100 meters through a flexible hose. So this would actually prove and complete our first stage of development. And then we go for the second stage of pumping system, which we proved at 400 meters, and we are going to make it 1,000 and then to further depths. To just give you an overview of the sort of life in the various resources, PMN, SMS, and CRC, you can see that they all are thriving place of life at these depths. And environment impact is a very, very serious aspect here. So the main stress comes from the protest is that we are going to damage an ecosystem which has never been disturbed for the last millions of years, and we have no idea what this impact will cause for the future, how it will affect our food chain. So the seabed disturbance, the plume generation, the underwater noise, underwater lighting, discharges into the water column, the interference in the photic zone. These are all things which are being addressed and also being studied into making it a more sustainable exercise. So what are the motivating factors, if you were to ask, what are the motivating factors to go for deep sea mining? To just put it bluntly, it's the hunger for the growth. The hunger for growth goes for hunger for minerals, and hence you have depleting source on land and you have to go to the sea, which are unexplored. The stress on renewables and green technology and the stress for high density batteries is what drives the metal requirement of nickel, copper, and cobalt. And with more stress to meet the climate change or the climate restrictions by going for electric vehicles, you require these minerals, and these are not available as much on land. The rising prices and the distribution of where the cobalt actually goes will indicate how these metals will be driving the deep sea mining initiatives. Now the question would be, which would be the most promising for anybody to enter? Will it be sulfides? Will it be cobalt crush? Or will it be nodules? Nodules is the low-hanging fruit as far as the technology goes, and the the quick implementation, because these are nodules that lies on the seabed. The only hitch is the depth. Otherwise, this is something which is easily manageable, much better than the cobalt crust or the sulfides. You can actually make out the interest from the number of contractors registered with the Intermittent Seabed Authority. For PMN, that is nodules, you have 17 contractors in the North Pacific, whereas for the SMS you have just 4 and CRC another 4. This is the costing or the abundance criteria. The nodule mining criteria has been set, that how do you decide that this particular area is fit or lucrative enough to mine. You have the grade, abundance, topography, mine life, etc. specified. And in the area, that Indian area, which is 75,000 square kilometers, this is the sort of estimate that has been brought out, that there is about $139 billion $139 billion worth of resources available